Good morning, everybody. Before I really start talking about the content of my presentation, I'd just like to point out that a lot of this work was enabled by a lot of people from the CANARY team, who essentially were funded by Opticon, which allowed CANARY to go back on Sky this summer. So particularly I'd like to thank people from Paris and Durham who spent a lot of time giving us this opportunity. And when I say us, the main PIs of the experiment were Maud Langlois from CRAL and my student Nicolas Dubost. Neither of them can be here today, so I'm presenting this work. Okay, so the background is that Opticon funded time on CANARY for experiments to give them the opportunity to be exposed to a real AO system on Sky. And in our case, we put on 2 wavefront sensing interferometers. So this is a wavefront sensing workshop. And the key points I'd like you to take away from this presentation are that we operated these interferometers in the visible part of the spectrum. And today I'm going to be really talking about some initial results. And it turns out the run was successful, but it was also challenging, and we're still doing analysis. For the first run of prototype instruments, this is not too surprising. Okay, so what I mean by wavefront sensing interferometers is very simply is that interferometers that can measure the phase directly. So they're not really measuring the wavefront. And so we're going to be using self-referencing interferometry. So this is where you generate the reference signal from the light itself, and you obtain the measurement in one exposure. So the advantages are that there's the reconstruction, there's no model required. You directly obtain the phase. And if you construct your instrument carefully and you have a sufficiently large strain ratio, then you can achieve both high precision and high accuracy. And then these measurements become scale-free, and what I mean is there's no difficulty with going to ELT scale, a large number of sub-apertures. So this is another one of the motivations. And so then this leads to the sort of our foreseen applications. I've got 3 examples there. Some of them have been spoken about at previous conferences. But the real 2 that are relevant for the CANARY experiment were measuring quasi-static aberrations and high-order wavefront sensing. So these 2 are sort of what CANARY allowed us to try inside the realistic environment. So just very briefly, self-referencing interferometers. I'm sure you're fairly familiar with the concept of the point-diffraction interferometer. But the essential point here is that at this plane, the focus, which is called the pinhole, I'm going to describe that as a beam splitter of sorts. And the beam is broken into a reference beam, which is spatially filtered. And so we measure the phase of the test beam relative to this reference beam. So for the Durham experiment, the way that we did this is there is effectively a grating. So we're going to call this a small angle beam splitter. This generates many modes at the focus, and we select 2, the on-axis and the +1 order, and there's a specially constructed filter that only permits these 2 orders through. They recombine, so you re-image the pupil, but it has these interference fringes superimposed on it. And so these interference fringes are the signal we measure and then we process to obtain the wavefront. So the alternative instrument we tested was the integrated Mach-Zehnder from Lyon. This operates essentially much like a Mach-Zehnder, so you split it into 2 arms. So this is your test arm, and then the other arm has a pinhole which generates the reference wave, and then you obtain 2 interferograms. And the advance in particular that has been made is that this entire section of Mach-Zehnder is now one solid block of glass. So this incorporates the beam splitting, the spatial filtering, and the recombination. And then there are 2 outputs. I have to be honest, I don't think it matters whether the outputs or inputs are here or here. It's a symmetrical piece of glass. And the scale for reference, this is about 50 millimeters. So it fits into your hand. Okay, so CANARY in 2019. Many of you will be very familiar with CANARY, many talks given over the years. This one's slightly more unusual because CANARY wasn't really the goal of it going on Sky. Rather, it's the experiments, and there were other experiments. And so we were offered this opportunity to expose our interferometers to the residuals, and we constructed a design that allowed both to be run in parallel. So we split the light between both instruments, with the concept being that they could be cross-compared. And the major change we made was that because we were limited to silicon detectors, we had to work in the visible part of the regime. Normally, CANARY allows through the AO-corrected beam is in the near-infrared to the infrared. And so this is the basic layout of the CANARY implementation that we used, slightly different to what has been done previously, but essentially on the Naismith platform, the focal plane has a tip-tilt mirror, an Alpeo DM, and then a 14 by 14 Shack-Hartmann. Here, only 10% of the light goes through, so 90% of the visible light is transmitted to the experiments. This is roughly what it looks like on the bench. So our DM is up here. This is where the wavefront sensor lives. This is the tip of the wavefront sensor. There's a relay and a filter wheel that we installed, and then the two interferometers are here, but this is the CAWS, and this is the Mach sender. I should probably point out, I haven't explained what the CAWS, complex amplitude wavefront sensor. Okay. The final part, there's a beam splitter here, leads to an on-axis imaging camera. So we have simultaneously the point spread function, the wavefront sensor measurements from the Mach sender, from the CAWS, and the on-axis wavefront sensor. So in principle, we have everything we need to do the cross comparisons and understand the environment that the instruments were exposed to. So the good things about CANARY and the bad things about CANARY from our perspective, it's built on a gravity-stable optical table, so it's very easy. It's almost like going into an optical lab, putting down your experiment, aligning it with its internal sources, and you go. So we literally took, in both cases, the laboratory experiments to the telescope, interfaced them with CANARY, and then we were able to receive the signals. And simultaneously, the software environment is very open, so it's very easy to introduce our computers and our software. The main constraints were funding and time, so that meant we had to work in the visible, and CANARY is limited throughput, fundamentally. It's an experimental testbed, and it's not optimized for visible SCAO. So in visible SCAO, the performance is not particularly good. STRO ratios of 5% if you're lucky. So it's quite a challenging environment, but it was also a very valuable opportunity. So just to emphasize what the signals we expect on the camera are, these are from the lab, and then these were from CANARY when operated with internal sources. And the CAWS, you have the fringe patterns as I explained before. Much like the self-coherent camera, when you do a Fourier transform, you receive three regions of the autocorrelation, and then we can select just one, shift inverse Fourier transform, and this is the phase of that inverse Fourier transform. By construction of the filter, these do not overlap, so the signal in this part is limited in bandwidth by that filter, but is completely distinguishable. For the Mach sender, it's slightly different. The two outputs, which are imaged side by side, are differenced and combined, and you retrieve the interference fringe directly. And then when you put them onto CANARY, we get the expected signals. We get the fringes, and this is the retrieval. And then again, something similar here, and then this is the retrieval. So the experiments were successfully interfaced. And so we had a three-step plan. So phase 0, we couldn't use letters. CANARY's already used letters, so we have to use numbers. So phase 0, can we actually get it working on the bench with static residuals? Phase 1, can we measure the residuals on Sky? And then what we haven't done in this run is phase 2, but is a future plan, is to use the retrieved phase from the interferometers and correct for the AO residuals. And that's simply because it wasn't possible. We didn't have the hardware. Okay, so the phase 0 for the CAWS. So the conditions, we are expecting these sort of Ströll ratios. This is the band we thought we were working in, but actually we found we were sort of centered more around 730 with 100 nanometers, and this was a flaw in our optical design. But this is actually a measured PSF. And then with a monochromatic source, and this is the monochromatic source, and you get very nice fringes. You can see an expected distortion of fringes. These two lines are alignment features within CANARY. And then this is the measured phase. No, it's been converted to wavefront. This is the measured wavefront. You can see there's an actuator which is not well controlled by CANARY because it's behind the obscuration. That had been removed for these measurements. So we do the same measurement with polychromatic light. You can see that it's blurred. It's blurred because there was a chromatic aberration in our relay optics. We didn't have time to optimize the design. And so that limited us to 100 nanometers of bandwidth. Because there's a significant defocus, these fringes become washed out. But if you do the retrieval and all the analysis, you get a very similar result. And then this is the difference. There are also a couple of phase points which are do not agree, but otherwise the agreement is very good. So we're very happy with that. My student, who's currently writing up in the next month or so, was very relieved. Everything appears to work. So for the Mach sender, a similar situation. It's important to note that you need very good tip-tilt control and NCPA correction to be able to operate either of these instruments, because you must focus light onto that pinhole to get the reference beam. And so we did further NCPA correction and then alignment, and then which was successful. And this is what you get within CANARY and the retrieval. This is after a demodulation scheme has been applied. So the normal problem with a Mach sender type interferometer is you're limited to minus pi over 2 to pi over 2. So you can't access minus pi to pi. But by introducing a small waffle mode, you can actually then extend that range. You can double the range to the full range that you need. And so here, a waffle has been applied to both images, here with 50 nanometers and here with 5 nanometers RMS. And that's sufficient to do the demodulation scheme. So with 5, there isn't a particularly big impact. And with 50, of course, you can see the satellite point-to-point functions around the image. Okay. And in this case, we use this demodulation. And so this is running through static residuals with the polychromatic source. And the change that you're seeing is due to bench turbulence. Okay, so we thought, fantastic, everything's working, we've got all the software, everything's synchronized, everything is aligned, we'll go on Sky. And then we found everybody's favorite feature, which is an unknown, I think, as Donald Rumsfeld once called it. So let's for the moment call it a detector problem, and we're still doing some analysis, but I'll show you what we found. So this was these were the best fringes we found on Sky. So I thought I'd submit this as you know, for the best image. You know, if I can convince you that there are images inside of here, then I probably have won. So okay. So we had a model for, based on the fact that behind an AO system, you should be able to integrate and receive coherently add up the fringes, so we should be able to get a signal. So these are quite a long exposure times. This is a second up here, but we thought we should be able to get above SNR of 1. We are limited by having a very poor detector. Again, funding constraints, time constraints. Unfortunately, we weren't able to take a high-quality detector on Sky. Our actual measurements of SNR are down here. We can't really explain them. They're in they sort of correspond to what we think they should be. And then these plots are very time-consuming to explain. But essentially, they're histograms.
When you say signal to noise of what?
Okay, so this is the signal to noise of the fringes. Well, exactly. They're below.
You put error bars suggest that you have a significance in the measurement of the signal to noise. You have an error bar
Yes.
on your signal to noise.
Yes.
That's where you plot it.
So those error bars represent the distribution of our estimates of SNR. So the design of the CAWS, because it has a bandwidth limit, the sampling of the fringes oversamples the fringes. So there are regions in the Fourier transform that contain purely noise. So from the central limit theorem, it becomes homogeneous. So you can extract noise, and you can extract what you think is noise in the signal from the region.
Measurement of your noise, not of your signal.
No, we think it's a good estimate based on simulation. Yeah. And so these three panels should show a histogram with the signal plus noise, the noise, and also the noise. And the fact that these two are different, but these two are similar in all cases, suggests that actually we've been contaminated by some artifacts. This camera issue wasn't obvious. If we went to, this is back to where we successfully have fringes with a monochromatic case, the very best we could have, and we have an SNR well above 1, then this corresponds to what we're expecting. So we'd never seen this problem before. Lesson learnt. For the Mach-Zehnder, it was more successful. These are measurements of the residuals behind CANARY, operating at 200 hertz. Now, there were significant tip-tilt residuals in the beam, which means that effectively the low-order signal has been washed out. So initially I thought this was a measurement of scintillation, but no, in fact it is the phase. And you can see some features like there's some, I guess, a actuator or some other feature up here that has become stuck. And if you look very closely, it takes a lot of studying, and perhaps I believe too much. You can see some interesting features around the vanes of the spider in the telescope. So cross-comparison, this was the real thing that we thought we could bring. We could bring both sets of instruments, and we could do a cross-comparison, and then we could have a confirmation that everything was okay. And we have got stuck in trying to understand our data, so we actually do not have anything yet to compare, but perhaps for CfAI next year. So fingers crossed. Watch this space. So our future plans. Two potential directions suggest themselves. One, infrared, where CANARY would have delivered a higher strain ratio, the turbulence would have evolved more slowly. Of course, that costs a lot of money, and we didn't have any suitable cameras. The other alternatives is to increase the strain ratio, which sounds more expensive, but there is a solution, which is that CANARY previously has hosted an upgrade. So this is a bench in Durham, and it sits above CANARY, and it receives some light, and it has a Boston 1K DM in it. So that we had previously integrated. We know that it works. It's in our lab. And so we are looking at integrating both interferometers onto this bench, and then hopefully being able to take that back to CANARY. Okay, and thanks for your time. And just this shows, very quickly, we've got one experiment here, but there's also another experiment, a spectrometer. So CANARY did quite a lot this summer.